Today we'll be discussing complex numbers. Let us solve the following equation. X squared minus 6x plus 10 is equal to 0. Well, we know how to solve quadratic equations. So if we have ax squared plus bx plus c is equal to 0, then the formula says that we have two roots that are given by minus b plus minus square root of b squared minus 4ac divided by 2a. So if we apply this formula here, then we get the following expression for the roots. So the roots are 6 plus minus square root of b squared, which is 36, minus 4ac, so that's 40, divided by 2. So that is 6 plus minus square root of negative 4 over 2. And here we run into a trouble because we have a square root of a negative number, and we know that square roots of negative numbers cannot be taken inside real numbers. This is the entry point to complex numbers. So we assume existence of a special number I with the property such that I squared is equal to negative 1. So clearly I cannot be a real number because the square of any real number is greater or equal to 0. But nonetheless, this equality says that I is the square root of negative 1. And then if we have square root of negative 4, then we treat it using usual algebra. So we write that this is square root of 4 times negative 1. So it's a product of square root of 4 times square root of negative 1. And square root of 4 is equal to 2. And square root of negative 1 is equal to I. And so what we get is square root of negative 4 is equal to 2i. And then we arrive to our answer. So here we get 6 plus minus 2i divided by 2, or this is 3 plus minus I. And we get two roots. So we have one root is 3 plus I, and the second root of this equation is 3 minus I. So these are the examples of complex numbers. Now we get a definition that a complex number is a number of the form a plus bi, where a and b are real numbers, and this I, which is called imaginary unit, satisfies I squared is equal to minus 1. The set of complex numbers is denoted by letter C, and so this is the set of expressions a plus bi, where a and b run over real numbers. Let us discuss addition and multiplication for complex numbers. Suppose we need to add two complex numbers. One is 3 plus 4i, and the second complex number is 1 minus 7i. So what we do is we carry out addition component-wise. So we write this is 3 plus 1 plus 4 plus negative 7 times I. And so this will be 4 minus 3i. For multiplication, we just expand everything. So here, if we multiply this by 3, we get 3 minus 21i. And then if we multiply this by 4i, we get plus 4i and minus 28i squared. And so we get 3 minus 17i and minus 28, but I squared is equal to minus 1, so times minus 1. So this becomes plus 28. And so then the answer will be 31 minus 17i. So it's clear how to generalize this for arbitrary complex numbers. And I leave it for you as an exercise. Show that addition and multiplication of complex numbers are commutative and associative. We plot real numbers on a line. How can we plot complex numbers? The answer to this is that we can plot complex numbers on a plane. So here we take a plane which we call complex plane. And this complex plane will contain a line of real numbers. So this horizontal axis is where the real numbers live. And on the vertical axis, we mark the imaginary unit. So I will be here, and minus I will be here. And then, if we have a complex number z, which is a plus bi, then we mark a on the real axis, and we mark b on the imaginary axis. So here, so this will be bi here. And so then, in this position here, so we get z, which is a plus bi. So the component a is called the real part of a complex number. So this is the real part. And component b is called the imaginary part of a complex number. So note that our convention is that the imaginary part of a complex number is a real number. Complex numbers were invented in Renaissance Italy, and at the time they were criticized for not being real. They cannot be used for measuring weights, distances, or amounts of money. Nonetheless, complex numbers proved that they're extremely useful, and they have a huge amount of applications, starting from computation of the lifting force of the wing of an airplane to other problems in air and hydrodynamics, then in telecommunications, in the study of electromagnetic waves, and it's not really possible to list all applications of complex numbers. The idea of applications of complex numbers is that often, even when the answer to our problem is real, we want to use complex numbers along the way, and some intermediate steps of our calculation will be carried out with complex numbers, and then the final answer will still be real. Another characteristic of a complex number that we will discuss will be norm. So norm of z. So this is denoted as the same way as absolute value. So this is going to be the distance to the complex number from the origin. So that is, it's a square root of a squared plus b squared. Another operation that we will study is complex conjugation. And it's denoted with a bar. So if z is equal to a plus bi, then the complex conjugate, z bar, is the complex number a minus bi. Geometrically, this is a reflection with respect to the real line. So here, if z is this number, then its mirror image here is going to be z bar, which is a minus bi. Note that complex conjugation does not affect real numbers. Complex conjugate of a real number is the same real number. And the complex norm of a real number is just an absolute value. We'll get square root of a squared. Let us list some properties of complex conjugation. So here we have the following lemma, that z plus z bar is equal to 2 times real part of z. And the second property is that the product of z with its complex conjugate is equal to the complex norm of z squared. Let us prove these properties. So suppose z is a plus bi. Then what is z plus z bar? So this is a plus bi plus a minus bi. So bi will cancel and we get 2a, but a is the real part of z. And so we get 2 times real part of z. So if we multiply z times z bar, then here we have a plus bi times a minus bi. And because addition and multiplication is commutative and associative, all our standard algebraic formulas hold true. And so we have a formula for the product of a sum with a difference. And so this will be a squared minus bi squared. And here we have a squared minus b squared times I squared. But I squared is equal to -1. And so this gives us a squared plus b squared. But that is the norm of z squared. The corollary of this is the following claim, that complex numbers form a field. Now, we have addition, multiplications, 0, 1, and we can easily verify all the axioms like commutative, associative laws, and distributive law. And the only tricky place is multiplicative inverses. So if z is not equal to 0, then the inverse of z is defined as z bar divided by norm of z squared. So which is a minus bi over a squared plus b squared. Clearly, this is a complex number because its real part can be written as a over a squared plus b squared, and its imaginary part can be written as minus b over a squared plus b squared times I. And these two coefficients are real numbers. So this is a number of the form something plus something I, where these components are real numbers. Now, to prove this corollary, we have to show that if we multiply this expression by z, we are going to get 1. So if we have z times z bar over norm of z squared, so this is equal to z times z bar over norm of z squared. But by this lemma, z times z bar is norm of z squared. And so we have norm of z squared over norm of z squared. And so this is equal to 1. And we note that if z is different from 0, this implies that norm of z is also different from 0, because a squared plus b squared is equal to 0 only when both real numbers a and b are equal to 0. Let us do a couple of exercises. Let us find what is the inverse of I. So by our formula, this is I bar divided by norm of I squared. So the conjugate of I is negative I, and the norm of I squared is 0 squared plus 1 squared. And what we see is that the answer is negative I. And indeed, we can easily check that if we multiply I with negative I, we're going to get 1. So this is minus I squared. So this is minus times negative 1, and this is equal to 1. As another exercise, let's compute what is 1 over 2 plus 3i. So here we take the conjugate of this number, so it will be 2 minus 3i, over 2 squared plus 3 squared. And so here we have 9 plus 4, that's 13, and we get 2 over 13 as a real part, and minus 3 over 13 times I. And so this is the inverse of 2 plus 3i. An immediate ramification of the fact that complex numbers form a field for us is that we can do linear algebra over complex numbers. All algorithms of linear algebra will perfectly run with complex numbers instead of real numbers. Next, we are going to discuss the polar form of a complex number. So this is a slightly different geometric approach to complex numbers. So here we consider the angle theta between the line towards the complex number and the positive part of a real axis. So we give the following definition. The argument theta of a complex number is the angle between z and the positive axis of a real line. And this is measured in counterclockwise direction. And the notation is that theta is argument of z. Now let us look at some examples. So what's the argument of 1 plus I? So the number 1 plus I sits right here. And we see that the angle is 45 degrees. So we say that the argument of 1 plus I is pi by 4. So if I have argument of 3i, so then this is on positive part of imaginary axis. And so this argument is pi by 2. So if we take argument of negative 3i, then so here we have to go in the clockwise direction. So we say that it's either minus pi by 2, or that's the same as 3 pi by 2. So when we measure angles, so as angles, the angle minus pi by 2 and the angle 3 pi over 2 are the same. So as angles, 2 pi is equal to 0. So as angles. So if we take real numbers, then argument of 2 is equal to 0, and argument of negative 2, so because now it's on the negative side, so this will be equal to pi. Suppose z is a plus bi. And so let us look at the norm of z. So let's denote the norm of z by r, and the argument of z, let's denote it by theta. So then we can express a and b in terms of norm of z and theta. So now norm of z is equal to r here. And so what we see is that a is equal to r cos theta, and b is equal to r sine theta. And then we can write z as r cos theta plus I r sine theta. or this is equal to r times cos theta plus I sine theta. So this expression is called polar form of a complex number of z. Let us explore the relation of the polar form of complex numbers with multiplication. Suppose we have two complex numbers written in their polar form. So suppose z1 is r1 times cos of theta plus I sine theta, and z2 is r2 times cos of phi plus I sine phi. So here r1 is norm of z1 and r2 is the norm of z2. Now let us compute z1 times z2. So this will be r1 times r2 times cos theta plus I sine theta times cos phi plus I sine phi. This equals r1 times r2 times, so let's expand this product. We have cos theta times cos phi plus I sine theta times cos phi plus I cos theta times sine phi, and plus I squared sine theta times sine phi. This becomes r1 r2 times, so here we have, let's combine this term with the last term because I squared is equal to minus 1. So we have cos theta times cos phi minus, because of I squared, sine theta times sine phi. And now we have plus I times sine theta times cos phi plus cos theta times sine phi. And now it's time to use our trig identities. So we see that this is a formula for the cosine of the sum. So we get cosine of theta plus phi, and this is the sine of the sum, plus I times sine of theta plus phi. And what we get is that we get another complex number in the polar form. And now we get the following conclusion. When we multiply two complex numbers, then their arguments add. So the argument of the product of z1, z2 is argument of z1 plus argument of z2. So here we saw that theta was the argument of z1, phi was the argument of z2, and the argument of the product is theta plus phi. And the norms, so the norm of the product is the product of the norms. So z1, norm of z1 times norm of z2. Because clearly the norm of this complex number is the product r1 times r2. And these were the norms of our factors. This gives us a geometric procedure for multiplication of complex numbers. Suppose we are given two complex numbers as points on a complex plane, and we want to multiply them using geometric methods. Construct a triangle joining points 0, 1, and z1. So here we take this triangle. Then as a second step, so construct a triangle that joins points 0, z2, and some vertex w, which is similar to the first one, to the first triangle. And in this similarity, so matching 0, 1 with 0, z2. So what we are doing is, so we join 0 with z2, and then we want to construct a triangle with a base 0, z2, which is similar to the first triangle, where this segment 0, 1 is now matched to segment 0, z2. So this triangle then will look somehow like this. So here we will have vertex w. Once we do this, we obtain that w is z1 times z2. So indeed, so if this angle is alpha, then the argument of w will be argument of z2 plus the argument of z1, which is alpha. And then from the properties of similar triangles, we can conclude that norm of w is the product of the two norms. And thus, the point w is the product of the complex numbers z1 and z2. Next, we're going to use complex numbers to derive some interesting trigonometric identities. Consider a complex number z with norm 1. Since the norm of z is equal to 1, in polar form, we can write it as cos of theta plus I sine theta. Let us consider the nth power of z. So this is cos theta plus I sine theta to the power n. Using this property, we see that the norm of z to the power n will still be 1. And because arguments add when we take the product, the argument of z to the power n is going to be n theta. And so we can write this complex number as cos of n theta plus I sine of n theta. So this will be the polar form of z to the power n. But we can also use Newton's binomial formula to evaluate this expression. So let's apply the binomial formula. So we get that cos theta plus I sine theta to the power n equals the binomial coefficient n choose 0 times cos to the power n theta plus the binomial coefficient n choose 1 times cos to the n minus 1 theta times I sine theta plus n choose 2 cos to the n minus 2 theta times I squared sine squared theta, and so on. The last binomial coefficient will be n choose n, cos theta will be to the power of 0, and we will have I to the power n times sine to the power n of theta. We see that even terms in this sum will be real, because so the first term is real, then I squared is equal to minus 1, so this will also be real. Then the term with I to the power 4 will be real as well, and so on. And odd terms in this sum will be purely imaginary. Now we have two expressions for z to the power n, and let us equate real and imaginary parts. So for real part, so here the real part of this expression is cos of n theta. And for the left formula, so here we're going to get cos to the power n of theta. Then we skip this imaginary term, and so the next one real term will be with I squared, but I squared is minus 1. So we'll get a negative sign, n choose 2, cos to the n minus 2 theta times sine squared theta. And the next term will be with I to the power 4. And I squared is minus 1, so I to the power 4 is equal to plus 1. So we'll get plus n choose 4, and we have cos n minus 4 theta times sine to the power 4 theta, and so on. And if we equate imaginary parts, so sine of n theta equals, so here we take the terms with I. So we'll have n choose 1 cos to the n minus 1 theta times sine theta. The next term will be with I cubed, and I cubed is equal to negative I. So we'll have minus n choose 3 cos to the n minus 3 theta times sine cube theta plus, and so we'll have an alternating sum of this kind. The formulas that we get here are called Moivre's identities. As examples, so if we take it n equals 2, then we get the formula for cos of 2 theta. So this will be cos squared theta. And then minus 2 choose 2 is 1, so minus sine squared theta. And, so this formula will stop here. And sine of 2 theta is, so n choose 1, 2 choose 1 is 2, and we'll have cos theta times sine theta. And so these are two well-known formulas for sine and cos of a double angle. And if we take n equals 5, then Moivre's formula will give us the following, that cos of 5 theta is equal to cos to the power of 5 of theta minus, then we have n choose 2, or 5 choose 2, so this was the coefficient 10. We will have cos cube theta times sine squared theta. And n choose 4, so this will be 5. 5 cos theta times sine to the power of 4 theta. And for sine of 5 theta, we will get, so 5 choose 1, that's 5 cos to the power of 4 theta times sine theta, minus, then 5 choose 3, that's 10 cos squared theta times sine cube theta. And then the next coefficient will be 5 choose 5, so this is 1. So plus sine to the power of 5 theta. This is our first application of complex numbers to something that's completely real. So here we're talking about trigonometric identities. Our next topic is called roots of unity. Here we want to solve the following equation. Z to the power n is equal to 1. To solve this equation, we write z in polar form. We write z is equal to r times cos theta plus I sine theta. Then, as we saw, z to the power n is equal to r to the power n times cos of n theta plus I sine n theta. And we equate this to 1. If we equate this to 1, we're equating norms and arguments. So from here, so it follows that r to the power n is equal to 1, but r here is real positive or real non-negative. And the argument n theta is equal to 0, but this is as angles. Now, for real non-negative numbers, there is only one solution of this equation. So from here it follows that r is equal to 1. But how about this equality of angles? So here, theta equals 0 is not the only solution, because really the angle 0 should be treated as a multiple of 2 pi. So we write n theta is equal to 2 pi k, where k is an arbitrary integer number. And then we get the expression for theta. So theta is then equal to 2 pi k over n. Here k is integer, but how many unequal angles this will give us? So if k is equal to 0, so this will give us theta equals 0. If k is equal to 1, this gives us 2 pi over n. But if we go up to k equals n, then we will get 2 pi n over n. That's the same as 2 pi. But the angle 2 pi is the same as the angle 0. So this means that the distinct solutions will be only when k goes from 0 up to n minus 1. And the value of k equals minus 1 will give the same angle as the value of k equals n minus 1. So we get the solution of this equation is z equals r is equal to 1, but theta is given by that expression. So we get cos of 2 pi k over n plus I sine 2 pi k over n. And here n is fixed, and k goes from 0 to n minus 1. And these numbers are called roots of unity. Let us plot the roots of unity for n equals 5. All of these numbers will have norm 1, so this means that they lie on a unit circle. And when k is equal to 0, so this actually gives us a number with norm 1 and argument of 0, so this means that this is 1. So 1 is one of the roots of unity. And so the next number, when k is equal to 1, will have argument 2 pi over 5 when n is equal to 5. So this number will be here. So we'll have z1 in this position. So where this angle is 2 pi over 5. And then the next number will have argument 4 pi over 5. So it will be here. And so what we will get is we will get the vertices of a regular pentagon. So this is how roots of unity will look like. So in general, we say that roots of unity form a regular polygon with n vertices. Now, let us look at roots of unity from the algebraic point of view. So what we see is that these are roots of polynomial z to the power n minus 1. Let us index the roots of unity as z0, z1, z2, z3, and up to zn minus 1. We have the following algebraic fact. If a is a root of polynomial p of x, then we can write p of x as a factor x minus a times some polynomial q of x. You have probably seen this fact in high school math, and we will be discussing polynomials and these properties in detail in the second year honors algebra course. This principle applies not only to real polynomials, but to complex polynomials as well. And this allows us to factor z to the n minus 1. So this is a polynomial of degree n. And here we have n roots of this polynomial. So these are roots of unity. So this gives us the factorization that z to the n minus 1 is equal to z minus z0, which is 1, times z minus z1, so which is given by this expression with k equals 1, times z minus z2, times all the way up to z minus zn. Now let us expand the right-hand side of this equality and compare the constant terms. On the left, the constant term is minus 1. And what is the constant term on the right? So this will be the product of constant terms in all factors. So we have n factors of negative 1. So we have minus 1 to the power n times z0 times z1 times z2 all the way up to zn minus 1. And we get the following proposition. That the product of roots of unity is equal to minus 1 to the power n minus 1. Now let us look again at this expansion, and now let us look at the term with z to the n minus 1. So let's compute the coefficient at z to the n minus 1 of the left-hand side and on the right-hand side. On the left, this term is not present, so we get 0 on the left. And on the right, so if we take z to the n minus 1, so this means that in n minus 1 factors we have to pick z, and in the remaining factor we pick the constant term. And so then we're going to get minus z0 times z from all other factors, then minus z1 and z from the remaining factors, and so on. And our conclusion is that the sum of the roots of unity is equal to 0, well, if n is greater than 1. Because if n is equal to 1, then the coefficient at z to the n minus 1 will be non-zero, because this will be the constant term. So for example, this says that if we pick these 5 vertices forming the regular pentagon on a unit circle with one of the vertices at 1, then the sum of these 5 complex numbers will be 0. As an exercise, let us solve the following equation. Z to the power 4 is equal to 1 plus I. What we do is we write the left-hand side and the right-hand side in the polar form. So we write Z as R times cos theta plus I sine theta. And 1 plus I is, so the norm of 1 plus I is square root of 2. And the argument of 1 plus I is pi by 4. So this will be cos of pi by 4 plus I sine of pi by 4. Then z to the power 4 is equal to r to the power 4 times cos of 4 theta plus I sine of 4 theta. And since z to the power 4 is equal to 1 plus I, we're going to equate norms and arguments. So we will have r to the power 4 is equal to square root of 2, and 4 theta is equal to pi by 4. But this is equality of angles, so we should really write pi by 4 plus 2 pi k, where k is in z. The equation for r to the power 4 has to be solved in real numbers. And so there is only one solution. R is equal to 8th root of 2. And the equation for theta is now solved by dividing by 4. So we'll get theta is equal to pi over 16 plus pi k over 2. And now, so what are the distinct values of k? So k could be 0, 1, 2, 3, and when k is equal to 2, and when k is equal to 4, this will give us 2 pi. And so this will be the same as the case when k equals 0. So what we get is that there are only 4 solutions here. And we get our answer is that z is equal to r times cos theta plus I sine theta. So r is 8th root of 2 times cos of pi over 16 plus pi k over 2 plus I sine of pi over 16 plus pi k over 2, where k goes 0, 1, 2, or 3. Our next topic is complex exponentials. Here we want to figure out how can we compute e to the I alpha. To compute this, I will assume your familiarity with calculus, and more precisely with the Taylor series. So the Taylor series for e to the power t is the following. So this is 1 plus t squared over 2 plus t cubed over 3 factorial plus t to the power 4 over 4 factorial, and so on. Now let us take t to be I alpha. Then we get e to the I alpha is equal to 1 plus I alpha plus I squared alpha squared over 2 plus I cubed alpha cubed over 3 factorial plus I to the power 4 alpha to the power 4 over 4 factorial plus I to the power 5 alpha to the power 5 over 5 factorial, and so on. Now, we see that even number terms are real because I squared is minus 1, and the odd terms in the sum are purely imaginary. So let us separate real part and imaginary part. So for the real part, we will have 1, then I squared is minus 1, so we'll have minus alpha squared over 2. Then I to the power 4 is plus 1, so we will have alpha to the power 4 over 4 factorial. Next term will be minus alpha to the power 6 over 6 factorial, and so on. And the imaginary terms, so we will have I times, so we will have here alpha. The next imaginary term will be I cubed, which is equal to minus I. So we'll have minus alpha cubed over 3 factorial. Then with I to the power 5, this is equal to I, so we'll have plus alpha to the power 5 over 5 factorial minus alpha to the power 7 over 7 factorial, and so on. Now we can recognize the Taylor series in each of these terms. So for the real part, we have a Taylor series for cos of alpha, and for imaginary part, we have a Taylor series for sine alpha. And in this way, we arrived at Euler's formula. That e to the I alpha is equal to cos alpha plus I sine alpha. In particular, e to the 2 pi I is equal to 1, because cos of 2 pi is equal to 1 and sine of 2 pi is equal to 0. And e to the pi I is equal to minus 1. We see that for any alpha, e to the I alpha has complex norm 1. So these numbers parameterize the unit circle in a complex plane. And so if argument is equal to alpha, then e to the I alpha is a complex number on a unit circle with the argument alpha. As alpha runs over reals, e to the I alpha will circle around the unit circle. If we need to exponentiate a complex number, which is not purely imaginary, then here we use the properties of the exponential function, that exponential of the sum is the product of exponential. So this will be e to the a times e to the bi. And e to the bi is expanded using Euler's formula. So we will have e to the a times cos of b plus I sine of b. Next, let us discuss diagonalization of matrices over complex numbers. Suppose we have the following matrix. A is 2, minus 2, 1, 4. In order to diagonalize it, we start with a characteristic polynomial. For 2 by 2 matrices, it's lambda squared minus trace of A times lambda plus determinant of A. So this becomes lambda squared minus the trace is the sum of diagonal entries. So this is 6 lambda, and the determinant is 8 plus 2, so plus 10. So the eigenvalues are the roots of this characteristic polynomial. And this is exactly the quadratic polynomial that we started this lecture with. And so the roots here are lambda 1, 2 are equal to 3 plus minus I. So this tells us that A cannot be diagonalized over real numbers, but can be diagonalized over complex numbers. In order to diagonalize a matrix over real numbers, we need to have real eigenvalues. And here, eigenvalues are not real. Now, let us compute eigenvectors. So let's take an eigenvector for the first eigenvalue, lambda, which is 3 plus I. So here we can see the matrix A minus 3 plus I times identity matrix. So this will be, so we subtract 3 plus I from the diagonal entries. So we'll have minus 1 minus I and 1 here, and minus 2 and 1 minus I. To reduce this matrix, we swap row 1 with row 2. So then we get the matrix 1, 1 minus I, minus 1 minus I, and minus 2. When we compute eigenvectors, we are guaranteed to have a row of zeros. So this tells us that if we do the operation row 2 new is row 2 plus 1 plus I times row 1, so then this row will be 0, 0. So we get the reduced row echelon form 1, 1 minus I, 0, 0. So here we see that we have a single free variable. So this means that we will have a single eigenvector. If we assign parameter t to the free variable x2, then the value of x1 will be I minus 1 times t. And so what we see is that our single eigenvector will be I minus 1 and 1. So this is for eigenvalue lambda 1, which is 3 plus I. The matrix that we are working with is real. And here we will use the following principle that I leave for you as an exercise. So let A be a real matrix and lambda be a complex eigenvalue of A. Then first part is that then lambda bar is also an eigenvalue of A. And the second part, if V is an eigenvector with eigenvalue lambda, then complex conjugate of V is an eigenvector for eigenvalue lambda bar. So we have seen explicitly that the first part holds for this matrix. So we saw that the two eigenvalues are 3 plus minus I. This is a pair of conjugate complex numbers. If we apply the second part of this principle, then we will get the second eigenvector for the conjugate eigenvalue. So what we get is that the following vector, minus I minus 1, 1, is an eigenvector for lambda 2, which is 3 minus I. To get this eigenvector, we change the sign at I in all places in this vector. Now we can write down the basis of the space C2 that consists of eigenvectors. So here the first eigenvector is I minus 1, 1, and the second eigenvector is minus I minus 1, 1. This gives us the change of basis matrix C, which is C, B to E, and here we put our eigenvectors as columns. So I minus 1, 1, and minus I minus 1, 1. And we also have the diagonal matrix, which is the matrix of our transformation in basis B. And this diagonal matrix has corresponding eigenvalues on the diagonal. So the first vector has eigenvalue 3 plus I, and the second eigenvector has eigenvalue 3 minus I. So this is the diagonal matrix that we have. And finally, we write the diagonalization formula. That A is equal to C times D times C inverse. And the inverse of this complex matrix can be easily computed using our usual formulas. As another example, so let us diagonalize a rotation matrix. R alpha, which is cos alpha, sine alpha, minus sine alpha, cos alpha. So what we know is that we cannot do this over real numbers, because unless alpha is 0 or 180 degrees, the rotation matrix has no real eigenvectors, because every vector is rotated by angle alpha, and so we cannot possibly get a multiple of the same vector. Over complex numbers, we can diagonalize this though. So let us start writing the characteristic polynomial. So we have lambda squared minus trace of this matrix is 2 cos alpha times lambda, and the determinant of this matrix is cos squared alpha plus sine squared alpha, and so this is equal to 1. So we get lambda squared minus 2 cos alpha times lambda plus 1. And to find the eigenvalues, we need to solve this equation. So the roots lambda 1, 2 will be 2 cos of alpha plus minus square root of b squared minus 4ac. So we have 4 cos squared alpha minus 4. And this is over 2. And so this becomes 2 cos alpha plus minus square root of, so here we have, if we have 1 minus cos squared alpha, this will be sine squared alpha. So here we get minus 4 sine squared alpha over 2. And so what we get is that lambda 1, 2 is equal to cos of alpha plus minus I sine of alpha. Or this can be also written in the exponential form. This is e to the plus minus I alpha. Now let's take the first eigenvalue, cos of alpha plus I sine alpha, and let us find the corresponding eigenvector. So we take A minus cos alpha plus I sine alpha times the identity matrix. So what we get is, so we subtract cos alpha plus I sine alpha from the diagonal. So here we will get minus I sine alpha minus sine alpha and sine alpha and minus I sine alpha. So if we assume that sine alpha is not equal to 0, then this simplifies to the matrix minus I minus 1, 1 minus I. And then, so this will simplify to 1 minus I. And we can see that the rows in this matrix are proportional. So row 2 is equal to I times row 1. So this means that the second row will be eliminated. And this gives us the eigenvector V1, which is the following. So it will be I1 for eigenvalue lambda 1, which is e to the I alpha. And applying complex conjugation, we get the second eigenvector for the conjugate eigenvalue. So we'll have the second eigenvector will be minus I1. So this is for eigenvalue lambda 2, which is e to the minus I alpha. Now we can form the change of basis matrix. So this matrix C is formed by our eigenvectors. So we'll have I1 and minus I1. And we have the diagonal matrix D, which is formed by placing eigenvalues on the diagonal. We have e to the I alpha and e to the minus I alpha. And we have our diagonalization formula, that the rotation matrix R alpha is equal to C times this diagonal matrix, so e to the I alpha 0, 0, e to the minus I alpha, times the inverse of matrix C. So in particular, we see that these two matrices are similar, and we can check that the properties of similar matrices hold. So in particular, the determinants of both matrices are equal to 1, and the traces of both matrices are equal to 2 cos alpha. And we see here that something that cannot be diagonalizable over real numbers suddenly can be diagonalizable over complex numbers. We saw that using complex numbers, we can solve any quadratic equation. But it turns out that this goes far beyond the quadratic equations. And there is the following theorem. Let P of x be x to the power n plus Cn minus 1 x to the n minus 1 plus Cn minus 2 x to the n minus 2 plus C1x plus C0, where Cn minus 1 dot 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 C0 are complex numbers. The first claim. Then P of x has a complex root. So that is, there exists a complex number z such that P of Z is equal to 0. And the second property is even stronger, that P of X may be factored over complex numbers. So that is, it has not just a single root, but by induction we can prove that it has n roots. And so P of X can be factored as x minus z1 times x minus z2 dot 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 x minus zn. This is an extremely powerful property of complex numbers. And let's give a general definition. So definition. A field F is called algebraically closed if any polynomial P of X in F of X of degree n may be factored into n linear factors. So the conclusion is that the field of complex numbers is algebraically closed. And note that the field of real numbers is not algebraically closed. So here, if we take a polynomial of degree 2, x squared plus 1, then we cannot factor it as a product of two linear factors. So we cannot factor it as x minus a times x minus b with a and b in real numbers. So we can do this over complex numbers, but we cannot do this over real numbers. Now let us see what are the ramifications of this theorem for the theory of linear operators. So let T be a linear operator from Cn to Cn. So linear operator. And let P of lambda be the characteristic polynomial of T. And we know that degree of this polynomial is equal to n, the dimension of our vector space. By this theorem, this characteristic polynomial may be factored. So we can write P of lambda as, well, the leading coefficient is minus 1 to the power n, and then we have factorization. Lambda minus z1 times lambda minus z2 dot 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 lambda minus zn. So this tells us that every linear operator T from Cn to Cn has a complex eigenvalue. And we know that every eigenvalue guarantees us an eigenvector. And so from here, we conclude that every linear operator over complex numbers has an eigenvector. So we note that this does not guarantee diagonalizability. Indeed. So if we take operator A, which is 2, 1, 0, 2, so here P of lambda is equal to lambda minus 2 squared. So we see that this characteristic polynomial does split into linear factors as guaranteed by this theorem. But we don't have two eigenvectors here. So here we have only one eigenvector. And for diagonalizability, we need the basis of eigenvectors. So, however, if characteristic polynomial of t has n distinct roots, z1, zn, which are not equal to each other, then t is diagonalizable. Because in this case, we will have one eigenvector for each root. And this will give us a basis of Cn consisting of eigenvectors. In this example, so the characteristic polynomial does factor into linear factors, but we don't have two distinct roots. So we have one iterated root. Of course, this is only a sufficient condition for diagonalizability, but it's not necessary. We could have diagonalizable matrices with iterated eigenvalues. We are going to study diagonalizability and generalizations of diagonalizability of operators in greater detail further in this course.